Hi guys, welcome to the fourth and final video of friction. The last one I just I divided the third video into two parts. One was what we finished off on, how much force do I have to apply when I direct forces at an upwards angle, and we realized that this upward force formula looked something like this, and resulted me basically in applying a force of 164.05 newtons in comparison to if I just push directly forward, which was somewhat less, I think 158.48 newtons. So in this video we're going to look at how does that compare to directing a downwards and forwards force in terms of how much force I have to apply in that specific scenario. So that's what we're going to unpack in this particular video now. So here I have the block, and we say, for example, that now I'm directing a downwards force. Let me just try and get that in a slightly better color. Let's say, for example, I was directing a downward force at some angle to the horizontal. Let's call this, well, we'll stick with theta for now. It's the easiest one to use. So in this scenario, if this was the force with which I'm pushing or pulling, since it's still a vector, remember some component of that is being directed downwards and some component of this force is being directed towards the left. The downwards component is, according to this, f sine of theta, and the leftwards component is f cosine of theta. Okay. Since motion would then occur towards the left, we'll say that there's some acceleration causing motion of the block towards the left, meaning that the frictional force once again is going to be acting towards the right. So this is the force of kinetic friction. So it's just going to be F sub k. So that looks a little bit messy. F sub k. Okay, so that's my horizontal forces taken care of. This block is also not going to go up or down. It's not going to start accelerating upwards or downwards. So there are some vertical forces, again same as what we did previously. There's a downwards weight force and there's an upwards normal force, right? They will tend to counterbalance each other because there's no net acceleration upwards. So again, just to kind of drive the point home, I would unpack the net vertical forces, forces in the y direction, and we said that they're going to equal 0 because there's no net acceleration going up or down. There are three vertical forces here that we have to account for. Again, I'm going to take anything acting upwards and to the left as positive. So the upwards force here is the normal force, and then the two downwards forces are, it's minus this weight force minus this f sine theta, and all of that is equal to 0. Okay, so if I take both of these elements to the other side, the normal force is going to be equal to the weight force plus f sine theta, and we know that the weight force is mg, so the normal force is equal to mg plus f sine theta. And again, I'm going to put a box around this because it's going to become important just now. So there's my box, and I'll just close that off. So again, that's an equation that I want to make use of in a second. The next component is to sum all the forces in the x direction. Since there's an acceleration into the x direction, the sum of forces will result in an acceleration, a net acceleration in the x direction. So the forces in the x direction is just this f cosine theta. Since it's going to the left, that's a positive component, so f cosine theta minus, again, I have this frictional force, minus because of the fact that it's acting in opposite direction, and that's going to be equal to mass times acceleration in the x direction. Now I have to unpack this frictional force again, as I did in the previous video. So the frictional force is equal to mu sub k times the normal force. In this case, it's mu sub k, and the normal force this time is mg plus f sine theta. So mg plus f sine theta. If we pause there for a second and just kind of try and make sense of this, so it's saying that the frictional force is equal to the coefficient of friction times mg plus f sine theta. The normal force, conventionally, when I just push in a straight line instead of an angle, means that it's just mu mg. So what does this plus f sine theta mean? It means that the force of friction is going to be larger than if it was just being directed horizontally. In other words, by me pushing into the ground, that in essence is adding to the weight of this block, therefore increasing the frictional force, since the frictional force is proportional to n. N is all of a sudden becoming larger by that amount that I'm pushing into the ground. Okay, so I'm going to substitute that into this formula over here, and then we're just going to unpack it. F cosine theta minus this mu sub k mg plus f sine theta, and then that's going to be equal to max. Okay, so just for some sake of time, I'm not going to change colors anymore. You know where this is coming from now. It's just coming from this. So this is f cosine theta minus, I'm going to multiply this out. This becomes mu sub k mg. A minus times a plus is a minus. Minus f sine theta is equal to mass times acceleration. I'm going to get all the when I multiply this out, sorry, I forgot something here. Mu k times that is going to be mu sub k f sine theta, and that's equal to mass times acceleration. Okay. Now I'm going to factor out all the equations that have an f in it, so this is going to go to that side. So this becomes f cosine theta minus mu sub k f sine of theta is equal to max plus mu sub k mg. Alright, so to factor out the f, cosine theta minus mu sub k sine of theta is equal to max plus mu k mg. And then finally I can solve for f, which just tells me that this is going to be mass times acceleration in the x direction plus mu sub k mg, and all of that over this cosine theta minus mu sub k sine of theta. Okay, and we are done. See, the more you do it, the easier it gets, right? Okay. So let's try and make sense of this one in comparison to the previous one. If I take you guys back there for a second, I'm just going to copy and paste this. So this is the formula that I'm interested in. This was when I was directing it at an upwards angle, and over here I'm going to paste it, and then I'm just going to move it out the way just for comparative purposes. There we go. So you can see essentially they're exactly the same formula. The top component is saying how much more force I have to apply due to the friction alone, right? Exactly the same. But what you would have noticed is that this bottom component has changed. There's a plus when I direct the force upwards, and there's a minus when I direct the force downwards. And what we saw also is that the smaller this number becomes, the larger the force will be. So it's all dependent on the angle with which I tend to push. But in essence, this number over here is becoming a smaller number in comparison to this one, meaning that I have to apply a larger force. we realize that the frictional force is also going to be larger than what it would be otherwise. I think we realized that in the previous one it was around about in the 60s, whereas if I just push normally it'll be around about 70. So once I start plugging some numbers in, we can start comparing values. So again, mu sub k is not going to be any different. It's 0.2. Mass for this system is 40 kilograms. Acceleration that I'm wanting to achieve is 2 meters per second squared, and the angle with which I was pushing is also 30 degrees. Okay, so let's try and solve for force. So that's going to be 40 times 2 plus 0.2 times 40 times 9.81, same as it's always been, not any different. And this is going to be the cosine of 30 minus 0.2 times the sine of 30. Okay, so once I calculate all of that, I sit with a number of 206.88 newtons, which is larger than what I had in the previous one, which was 160 odd something. Okay, so it's due to this fact that part of my force is actually pushing this object into the ground, which is increasing the friction. So what I want to do next is try and just get an idea of what this frictional force is. So plug in the numbers that I have. It's just 0.2 times 40 times 9.81 plus that force, 206.88 times the sine of 30. I'm just going to do it on my calculator quickly. So 0.2 times 40 times 9.81 times 40 times 9.81 plus 206.88 times the sine of 30, and that equals 99.18. So 99.168 newtons. So you can see that the frictional component of the force has definitely increased. So normally if I just pull horizontally without angling it at all, it's around about 78. So this is about 21 newtons more frictional force that I'll experience due to the fact that I'm pushing down and into the ground. So hopefully that all makes sense and that it's not like drastically confusing. I would never expect you guys to derive these formulas. This isn't a maths class or anything like that. Yes, it's physics related, but it's more about trying to understand what the formula itself actually means, and how angling forces affects the frictional force, but also affects how much force you have to apply in a given scenario. So hopefully that makes sense, and hopefully that's given you guys some intuition and insight into how friction tends to behave and the factors that tend to affect it. Cool. See you guys next time.